Мэдээллийн тохиолдол бол малчид энэ туйлын бас хангалт хөвж ойлгож байгаа. Зүгээр орон нутаг засаг захиргааны байгууллагаас тухайн үеийн одоо нэг цаг агарын урьдчилан сэргийлэх мэдээг бол одоо байнга өгдөг. Одоо урьдчилан сэргийлэх үнэхээр одоо цасан шуурга, тийм шорон шуурга, цаг агарын одоо тийм хүнд нөхцөл ийм байдлуудыг бол байнга одоо мэдээж ажиллаж байна.
When examining options to mitigate further livestock mortality during extreme weather events in Mongolia, the Gobi Forage team, led by Dr. Jerry Stuth at Texas A&M, decided to focus on building a large-scale early warning system that provides information about what areas of the Gobi Desert are showing signs of impending problems.
I would say that it's the combination of the nutritional status of the animal and the food that animal has to eat. That is a snapshot of what's happening currently and what's going to happen in the future.
The Livestock Early Warning System is divided into two major arenas of forage information, quantity and quality, that cumulatively can give a good indication where and when there's going to be a problem. Quantity is determined by a sophisticated computer model called FIGRO that models how plants grow. In combination with satellite imagery, near real-time maps of forage conditions can be created.
There's been random points assigned by IMAC or province to the Gobi. So what we do is locate the point as close as we can, and the point's only an 8-kilometer square grid. Then we put out our transect line, and he's just recording what it hits on and the species that it hits on.
With good data showing the variance of plant biomass for each of the selected points collected, it is possible for the FIGRO team to start building the simulation for the entire Gobi region. The FIGRO model needs other layers of information like the number and type of grazing animals and how much rain the area is receiving.
We use a product that's called CMORPH, and it's a product that's put out by the National Oceanic and Atmospheric Administration by the U.S. government that gives us the amount of rainfall that occurs in this region of Mongolia on an 8-kilometer by 8-kilometer square basis. What we're trying to do with FIGRO is mimic what Mother Nature does. You get rainfall that comes in, and you get sunlight that helps the plant grow. The plant needs soil to grow in, so we have components in the model that allow us to try to simulate what happens in the soil. Then the plant itself has components that a grass is much different than a shrub, so the model is capturing those things. And then lastly, the animals that graze the landscape have different preferences for grasses, shrubs, and forbs, and so as the model runs, it tries to mimic how those animals would eat that plant. So one of the other things that we're curious about is what's called the normalized difference vegetation index, and it's what the satellite sees from the sky as greenness, and so it's also known as a greenness product. The greener it is, generally the more biomass that's out there, and so what we try to do is use the NDVI to help us build these surface maps. And so this map that I showed you of available forage is built from the relationship between the NDVI and our modeled forage, and then we spread that forage amount across the region.
Now researchers must ask the question, is the computer really predicting the amount of forage out there? The solution is another team sampling hundreds of verification sites across Mongolia.
We will start a transect and walk 25 steps, and then we'll drop a quadrat. It's a half-meter square, and we'll clip all the vegetation within that half-meter square, put it in a bag, take it back to the lab, air dry it, weigh it, and then that can be aggregated up to a kilogram per hectare basis, and that gives us a value for the forage amount. We collect 10 of those, and that allows us to have a statistical mean and get an estimate of the variance, which allows us to see what the variability is in the sample that we collected. And that way, when we compare the model results, we know that we can have plus or minus some amount, and if it falls within that, we know we've fallen within our sampling error at the site.
Get in the car.
With the verification data collected, the Texas A&M team are confident that the model is accurately predicting forage quantity.
The missing piece of that puzzle then is what's the quality of the forage, how much protein, how digestible is that forage, and does that meet the needs of those animals to maintain some economic level of productivity.
In the United States, diet quality is determined by a technique called near-infrared spectroscopy. This procedure compares the chemical makeup of manure between the on-site animals of interest and lab animals that have been carefully fed diets of various qualities.
What we will do on our normal procedure here in the States is that we send out these styrofoam mailing boxes to our producers. They'll send us a sample in a plastic bag or a whirl pack like this that will go into an oven and be dried overnight at 60 degrees. We'll come back then with this on the next day. We'll grind those down to a 1 mil particle size. On the second day, the dried samples are taken out of this oven. And they'll be placed in a desiccator to come down to room temperature for about an hour. At that point then, we will place the dried ground material into these quartz lens. We'll get a sample presentation like this. We'll take the sample and place it into the machine. So this is what our spectrum would look like after we scan. We've got the visible portion of the spectrum here, the color that we normally see, and then the NIR portion of the spectrum there. What we've been able to do with the fecal NIR is to allow the animals to go out and select their diet and then relate the chemistry of the feces back to the diet. And we can do this through calibration equations. We can use fish-related animals, we can use stall-fed animals with hand-composed diets that we think will simulate the diet as best that we can. And by taking the known chemistry of those diets and relating that to the NIR spectra of the feces, we can build calibration equations that will allow us then in the future to just take the fecal samples, do the NIR, and then predict the quality of the diet. So given that we have the vast distances to cover, the poor road infrastructure in Mongolia, we're going to adopt this idea that we're going to take the lab to the people. So we're going to try to squeeze this benchtop type laboratory setup down into a box that we can put in a vehicle, and then we're going to drive that vehicle on a route through the country that the herders will know when it's going to be in their area, and they can bring their samples to that. What that allows us to do then is to take our quantity measurements, our stocking rate and our grazing pressure, put that with some quality measurements, and then through some software packages that we have called NutBow, marry those concepts together. We have the quality of the forage, we have the quantity of the forage, we have the needs of the animals. We're able to put all that and do the math and determine if this forage resource is meeting the needs of those animals, and if so, then we're doing good. If not, then we have different decisions that are available to us.
The information provided by the Livestock Early Warning System has the potential to relieve further weather-related livestock deaths across the entire Gobi region. It should be made available through many sources: satellite TV, radio, and government services.
Getting that information to the right people that make decisions is critical, and I think putting this in a formalized fashion through maps and other quantitative information that it will be useful to both government and herders.